Let's have the first example. Write a program that waits 14 machine cycles in normal mode, no compare match, and toggle PB5 after this delay continuously. Okay, so first thing that we need to do is we need to think about and calculate how 14 machine cycle is going to be done or understood by the AVR. So 14 machine cycle means in hex, it's going to be 0 hex 0E, 14. Okay, so this is the value that we need to consider. And we know that with an 8-bit timer, the maximum value that we can have is FF, which we were counting TC and T up to FF and then overflow. So we had to subtract 14 machine cycles from FF in order to find out how many cycles or how from where do I need to start the TC and to count up to FF. So when you do a subtraction, this is going to be 1 and that's going to be F. Now, we need extra 1 clock cycle for the overflow, and this is going to be F2. So this will be the value that we need to load into our TCNT in order to perform the operation. So now we know the TCNT value. TCNT 0, it's going to be 0 hex F2. So from F2, we have to count up to FF. Okay, so this is what is going to be happening. And we also need to configure the TCCR register, TCCR 0. Okay, so these are zeros. I just need to specify that it's not O. Okay, so TCCR 0 needs to be configured in order to have it in normal mode. Okay, and no pre-scaling. So if we look at this one, that's going to be, will be 0. The mode, it's going to be a normal mode. Comms, they don't need to be set. And clock select, it's going to be 001 because we don't need any pre-scaling over there. So we can easily see that TCCR, it's going to be set as 0 hex 01. Okay, so that will be our TCCR value. Now, do we need anything else to set up? The two important registers that we need to configure are these ones. So we don't need to configure anything else. We'll configure the ports, we'll configure the timer, and we will look for if it's overflowing or not in normal mode. All right, then. So let's see the procedures that we need to follow. So we have to set, because as we are going to toggle pin B5, we need to set this one to be an output port, especially the pin B5. And then we have to load the timer counter with the value F2. And it has to be in normal mode, no pre-scaling or nothing. And we have to loop until the timer overflows. Then we have to stop the timer, clear the flag, and toggle PB5. So that will be the algorithm. So let's write the code for it. Okay, so if we start, we'll have to start from .include M128 definition.inc file that we need to include with our AVR definition file. So then we have to define port B to be an output port, or port B bit 5 to be an output port. So bit 5 is, if you can think about it, I'll just write a comment over here. So 00 bit 5, and then we have got 4 more bits. So bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7, and bit 8. In this case, I have to say this is equivalent to hex to 0. Okay, so what I need to do is LDI R16 0 hex to 0. So this will be setting up the value for DDRV. Or if we want, we can actually set the SPI bit. That's also possible. So we can use that one as well. So LDI R16 hex 20. And then we need to have SPI DDRB 5. So PB5 as an output. We can use that one. And then LDI R17 0. And we need to clear the port B before we do anything else. So port B R17, clear port B. Now, the first thing that we are going to look at, we have to load the TCNT value. Okay, so this is going to be LDI R20 and then 0 hex F2. Now this will be loaded into the TCNT. As you can see, we are using out again because it's a special function register in IO registers. So that will be R20. So load timer 0. Then we have to load the TCCR. So I'm using R20 again, 0 hex 01. That's going to be the TCCR value. So I can say timer 0, normal mode, internal clock, and that will be out TCCR 0. By the way, this should be TCNT 0, TCCR 0, and that's going to be R20. And we already written the comment up there. And now we are set with the timer. Next thing to do is we have to monitor the interrupt flag. So we have to monitor the overflow flag, not the interrupt flag. We have to monitor overflow flag. So there are two ways of doing this. Either we are going to use interrupts or we are going to use polling. Polling means we have to, as a software, keep checking if that flag is raised or not. If we are using interrupts, we can do something else while the hardware is generating that interrupt flag when the timer overflows, and we can do something else at that time. But if we are not using interrupt, that means we have to use polling. Okay, so if we use polling, we have to check the TIFR register. So I can say in R20 TIFR, let's load TIFR into the GPR register, read TIFR, and then what we can do is we can use SVRS instruction and we can check the bit if it is set or not. Okay, So bit 0, if it is set in R20, then we do something else. Now, what we can do over there, we can say if TOV0 is set, skip next instruction. Okay, so what are we going to skip? Let's say R jump again. So if it's not set, we have to go back and wait over here until it gets set. Okay, that's why we need to do this. This is called polling. Okay, so if this is set, we have to skip this instruction. If this is not set, it will just go back and recheck until it is set. So when it is set, what are we going to do? LDI R20 0 hex 0, and that's going to be out TCCR 0 R20. This means we have to stop the timer when it is set. Okay, so we have to stop the timer. Then another important thing that we need to do is we have to clear that flag that is set, and this is done by setting that flag to be 1 by clearing it. So this is a little bit tricky over here. In AVR, if you want to clear a flag, you have to set it to 1 in order to clear it. So we can say that LDI R20, you can use this notation, 1 shift left the TOV 0. Okay, so the first bit of the TIFR, which is TOV 0, will be set to 1 in order to be cleared. So this is like 0 hex 0 1. Okay, so that's set. We cleared the flag, and I can say out TIFR R20. So clear timer overflow 0 flag. And then only thing that it is left, once we have done that for 14 machine cycles, we have to toggle, because it's asking us to toggle PB5. All I need to do is I have to do a toggle. I can do it with XOR because it was set to 0 first. Then if I XOR R17 with R16, which I already set it to 2, so it's going to be 0 XOR bit 5. Then this is going to be toggle bit 5 of R17, and then I have to send this out to port B R17. So that means toggle PB5. And then R jump begin. So where do we need to jump back? We have to jump back where we configured the timer in order to perform this 14 machine cycles. So this is how we can implement the 14 machine cycles in the normal mode with a timer, and then toggle PB5 after this delay. So we count up to 14 machine cycles, we wait, and then we toggle it. So this is a simple example of how we can use the timers. And this is in the assembly mode. Let's now create the C mode as well, just to see how we can use C. So I'll just directly start with DDRB. So we have to set bit 5 to be 1 so that it can be an output port. And then port B, we can say, we can end this with toggle Okay, it's difficult to find the tilde. Okay, it's not there. So that has to be inverted actually. Okay, I'll just put something in front of it so that we make sure that it's inverted. Nope. Okay, I use minus, but it has to be invert sign. Okay, so then we can say this is going to be PB5 equals 0. So we are setting it to 0 at the beginning. Now, while it is 1, let's open the braces and say TCNT 0. We have to set TCNT 0 hex F2 and TCCR 0 to be 0 hex 01. So while we have to check the TIFR flag, TIFR register for the flag actually, TIFR 0, sorry, TIFR and then 1 for the TOV 0 flag, then if it is equals 0 or not. So while it is 0, we hold over there. If it's not 0, then TCCR 0 will be 0. If it is set, we stop the timer. Check the TOV 0 flag, stop the timer, and then clear the timer TOV flag by setting it to 1. Semicolon up there. So once that is done, we just need to toggle port B. So port B, bit 5. And that's it actually. So we can close the bracket and that's all. So, okay, we have more lines in the assembly, but as I already said, we have to learn assembly as well. C is simple. We just need to set the port, then set the timer, check the flag. If it is set, clear the flag, stop the timer, clear the flag, and toggle port B. So you can also find these in the lecture note, the assembly version and the C version. Now the question is, how do we calculate the delay generated by the timer? Now, one thing that we can do is, which we have already done this, which is an inaccurate version of it. So if we assume clock is, let's say, 10 megahertz, okay, and then the period is 1 over f, which is 1 over 10 mega, which is 0.1 microsecond. This is our period. Now, the number of machine cycles that we are having is 14 machine cycles, which was given in the question. Or you can just use the calculation that we have done. So in this case, if we want to calculate 14 machine cycles, then 14 times 0.1 microseconds, which is going to be 1.4 microseconds. Now, this is the inaccurate way of calculating this delay. So first thing to do, calculate how much machine clocks last, which we already know that. Then calculate how many machine clocks it waits. And then we have to calculate the delay based on the period times the number of machine cycles. So ignoring the instructions overhead, and to obtain the approximate or inaccurate delay, let's say we have to calculate the period, which we already done it. So 10 megahertz, 1 over 10, 8 megahertz, 1 over 8. Divide the desired time delay by the period of the clock to obtain the number of clock cycles. And perform 256 minus n, where n is the decimal value we got in step 2 for the number of clock cycles, and then set TCNT equals 256 minus n. And this is the inaccurate calculation for this, but in order to calculate it accurately, now the timer delay, we know that timer delay is 1.4 microseconds based on our calculation. Now we have to also find out instruction execution delay. If you do remember, we have to count the instructions, which they are normally given in the data sheet. So what we need to do is we have to have these instructions to be counted, okay, which the total is 17 clocks in the loop, okay, so 17 clocks in the loop. That will give us delay as 17 times 0.1 microseconds, 1.7 microsecond. Now, as we have found 1.7, then total delay is going to be 1.4 plus 1.7 microseconds, which is going to be 3.1 microseconds as the total delay. So one thing that we need to understand is the wave of the period at PB5, because we are toggling. So how much it's going to be on, how much it's going to be off, on and off, and so on. Okay, so this is actually specifying these portions. Now 3.1 is there and 3.1 is there. So 3.1 low, 3.1 high. Low, high. That means 3.1 times 2, which is going to give us 6.2 microsecond for a wave period. So 6.2 microseconds is the wave period, and in order to find the frequency, you just need to divide that with 1, and this is going to give us 161.29 kilohertz frequency for the wave generated at PB5. We can actually generate waves like this by using these calculations. Okay, so this is how we use a simple example, and we can derive the calculations related with the machine cycles, the total delay, and the wave period, and the frequency of the wave. And yet another example that we can give, rather than writing a code, we have a code. So find the delay generated by timer 0 in the following code. Do not include the overhead due to instructions. Now, okay, so what do we need to look at? We need to look at the value loaded into the timer 0. So the TCNT value loaded into timer 0 is 0 hex 3E, as you can find it over here. Now, what is that 0 hex 3E? We can do that as FF is the maximum that we can have minus 3E, which is going to be 1, and 15 minus 3 is C1. So then plus 1 for the overflow, that's going to be 0 hex C2, not C3, C2, which is equivalent to 194 in decimal. So if we are using 8 megahertz clock, 8 megahertz is actually giving us 0.125 microseconds period. You can calculate that. And 194 times 0.125 microseconds will give us 24.25 microseconds. Okay, so this is the delay that we can calculate it. Or if you want the alternative way of doing this, TCNT is hex 3E, 0 hex 3 in decimal is equivalent to 62. And we know that 256 is the largest FF that we can have. 255 plus 1, 256 minus 62 will also give you 194. So this means that the timer counts from 0 hex 3E to hex FF, and plus the rolling from FF down to the 0. We need 194 clock cycles to do that. And each clock cycle is 0.125 microseconds because of 8 megahertz clock. Therefore, we can have 194 times 125, 24.25 microsecond width of pulse. So this was the example, which is important in order to understand how we can use these timers in order to calculate a delay or use these delays. So another example. So we have got, let me clear this. We have got a 10 megahertz clock rider program to generate a square wave with period of 10 microseconds on port B3. So before I carry on, let's do the calculations before we write a code for it. 10 megahertz, it will give us 0.1 microsecond period. That's fine. So the wave period that we are looking for is 10 microseconds. So 10 microsecond means when we consider the wave, oops. So this point to here is 10. That means this is 5 and this is 5. Okay, so 5 microsecond each, high and low pulses. So 5 microsecond divided by 0.1 is our clock period that we are looking for. This will give us 50 clocks. So 50 clocks is the value that we are looking for, and we know that with an 8-bit timer we have up until 256 minus 50 clocks. This will give us 206 as the TCNT value. So TCNT0 will be equivalent to 206. This is going to be loaded into our timer. And again, as it didn't specify, we can just use the normal mode. So TCCR 0, it's going to be once again 0 hex 01, normal mode, no prescaler, nothing over there. And rest is similar to what we have done, and we have to put this onto port B3, which is the pin 3 or the port 3 of the port B third bit. So the rest will be the similar of what we have written, and I can just show you the code here and how we need to configure it. So we can set these up, TCCR and everything. So VGM modes, if we go back from here, now if it is 01, it's CTC. You can use CTC as well. Okay, but if you are using CTC, then we have to think about the OCR value. So let's do it with normal mode first, and then we'll do with the CTC as well. So 206, which we have found for TCNT, loaded into TACNT. Port B with pin 3, PB3 as an output. We cleared port B at the beginning. We have to toggle it, so high and low pulses. Load timer, configure timer, control register, timer 0, normal mode, internal clock. And then we do a polling, read the TIFR register, timer overflow flag. If it is set, we skip to the next instruction. If it is not, we have to wait until it is set. Once it is set, we have to stop the timer. We have to clear the flag, and we have to toggle by using an XOR. So 8, which is the bit 3, with the 0, so that it's going to be high and low pulses, and that will be sent to port B. So it's similar to what we have done. We just need to calculate a different TCNT value in order to be loaded over here. Now, one thing that we need to change, by the way, this is the C version of it. Now, if we want to do this in CTC mode, there's one thing that we need to take care in CTC mode. Now, CTC mode is looking for the, rather than TCNT, we have to load OCR0 register. And in order to load the OCR0 register, so what we have found over here, we have got 50 clocks. Okay, so how do we calculate 50 clocks? 0 to 49 will give us 50 clocks. Okay, so I have to set OCR0 to be 49, because what we have seen is starting from 0 going up to 49, when the TCNT matches to OCR0, then we set the OCF0 flag. Okay, so that means this is going to be 49 set, and the VGM01 has to be 1 in order to have the CTC mode. Okay, so for CTC mode, VGM01 has to be set to 1. So this is what is showing over here. That is set to 1, and that means our TCCR0, it's going to be 0, 0, 0, 0, and then 1, 0, 0, 1, which is equivalent to 0 hex 0, 9. and this has to be loaded into TCCR 0 register. So what else do we need to monitor? In TIFR, we have to monitor OCF 0 flag, if it is set or not. So if we change this to CTC mode, now it's going to be from 0 to 49. That's why we have to set OCR to be 49 or 50 clocks, because we have to configure those. TCNT starts counting. When it reaches to 49, that means, okay, it reached to 49. They are equivalent to each other. Set the flag. So TCCR is configured and OCF0 will be monitored. So we made the modifications. 49 is loaded into OCR and hex 9 is loaded into TCCR, and we are monitoring TOV, this has to be changed. This has to be OCF0 flag. Okay, so OCF0 flag has to be monitored. So example 3, how do we modify TCNT0 in example 2 when in normal mode to get the largest time delay possible with no prescalers? And find the delay in microseconds in your calculation. Do not include the overhead duty instructions. So how do we get the largest possible delay? So with an 8-bit timer, that means we start counting from 00 up to FF, or 0 to 256. So the largest possible delay that we can have to count from 0 to 256. Sorry, 255 flux overflow 256. Let me do it that way. Plus 1. So we have to calculate from 0 to 255 in order to get the largest possible delay. So we know that when it reaches there and it overflows, we have got the largest one, roll over to 0. So that means my TCNT in normal mode has to be set to 0 so that I can have the largest possible delay. And the rest is just same. So if we calculate it again based on the 10 megahertz, which will have 0.1 microsecond delay period, if we have 256 in total times 0.1 microsecond, this will be 25.6 microsecond delay that we are going to get. So this is the largest possible delay that we can have if we set the TCNT value to 0 with 8-bit timers.